Today we're going to be looking at rolling without slipping. So when we talk about a pool ball rolling on a table, or we talk about a bike tire rolling on the road, that's the type of thing that we're going to be talking about today. Our goals today are going to be to learn about the rolling constraint. So how do we link the translational motion with the rotational motion of a rolling object when it's not slipping? We're going to be looking at two different ways of looking at rolling. One where we're looking at the translation of the center of mass plus rotation about the center of mass. And the other is rotating about a fixed point of contact. Finally, we're going to use our rolling constraint to solve rolling problems with force and torque. Rolling is a combination motion. As you can see in this diagram, we have the translation of the center of mass, that's labeled the path of the center of the wheel, and we also have rotation happening. That little red mark is actually rotating around its center of mass, and you can see in this picture the path of the wheeled rim. A point on the rim traces out a cycloid. You don't really have to know that for any other reason than that you can call it a name. But what is important is making a link between the velocity of the center of mass and the displacement of the center of mass. Like always, distance equals rate times time, so the displacement of the center of mass is equal to the velocity of the center of mass times time. In this case, if we consider the time to be one period of rotation of the object, we can say that the center of mass has actually traveled a distance of 2 pi r, the circumference of the circle. So if you can see, if we roll out the circumference of the circle, if we take this line and we straighten it out along here, the center of mass will have traveled one circumference length in the time of one rotation, or the period of rotation of this object. The rolling constraint links translation and rotation for objects that roll without slipping. As we saw earlier, delta x of the center of mass equals the velocity of the center of mass times the period, which is equal to 2 pi r. We can rearrange this formula to solve for the velocity of the center of mass, and that's equal to 2 pi over t over period times the radius. 2 pi over t is the angular velocity of the object, so we can replace 2 pi over t with omega here. So we finally get the formula, the velocity of center of mass equals the radius times the angular velocity. And this can be used as long as we're rolling without slipping. It will not be true if we have any kind of slipping happening, like if we're skidding on the road, or if you have a pool ball that's shot at such a velocity that it slides along the table before rotating without slipping. We can extend this rolling constraint to talk about other translational and rotational variables. We saw on the last slide that the velocity of the center of mass is equal to r omega. If we were to take the derivative with respect to time, we could get that the acceleration of the center of mass is equal to r alpha. If instead we integrate this formula, v of the center of mass equals r omega, then we would get that the displacement of the center of mass is equal to r delta theta, and that's just from the arc length formula that you already know. Okay, now we're going to try an example, and this is a very simple example using constant acceleration and constant angular acceleration. This is from example 10.4 from your textbook, and it says a bicycle slows uniformly from v initial equals 8.4 meters per second to rest over a distance of 115 meters. Each wheel and tire has an overall diameter of 68 centimeters. Now, don't forget to change that into a radius. Determine A, the angular velocity of the wheels at the initial instant t equals 0. B, the total number of revolutions each wheel rotates before coming to rest. C, the angular acceleration of the wheel. And D, the time it takes to come to a stop. For part A of this problem, let's consider that we're going to be in the frame of reference of the bicycle, so we're sitting on the bike, and the ground is initially going past us at a speed of 8.4 meters per second. That's the initial velocity of the bike. And since the tire is in contact with the ground at any moment, then a point on the rim of the tire is moving at the speed v equals 8.4 meters per second in the reference frame that were of us on the bike. So that means that omega naught, the initial angular velocity, is equal to v naught over r. We got that from the formula relating omega and our translational and our rotational variables, and that's going to be equal to 8.4 meters per second over 3.4 meters, the radius, and we get an angular velocity of 24.7 radians per second. In part B, since we know that the bike travels 115 meters on the ground, that means that because the tire is in contact with the ground at all times, a point on the edge of the rotating tire travels 115 meters total. So since each revolution corresponds to a distance of 2 pi r, we can calculate the number of rotations or the number of revolutions the wheel makes while it's coming to a stop by saying 115 meters over the circumference of the circle, 2 pi r. And since r is 0.34 meters, we get that this travels 53.8 revolutions. In part C, we're looking for the angular acceleration of the wheel, and so we know that omega naught is equal to 24.7 radians per second. We know omega final is equal to 0 radians per second, and we have to figure out how far it goes through delta theta. We can say that theta is 2 pi radians per 1 revolution times 53.8 revolutions, and that would give us 338 radians. Another way of looking at that might be that looking at the relationship between angular and translational quantities to say that theta is equal to L over R, or 115 meters divided by 0.34 meters, which would also give us the same 338 radians. Now what we're trying to find actually is the angular acceleration alpha. So given these quantities, we can use the formula omega final squared equals omega naught squared plus 2 alpha delta theta. So alpha is equal to omega final squared minus omega initial squared over 2 delta theta. When we plug in numbers to this, we get that alpha is equal to negative 0.902 radians per second squared. Finally, in part D, we can use some of the same known and unknown quantities. We can say that Omega initial is 24.7 radians per second. Omega final is 0 radians per second. Probably the easiest thing to do mathematically would be to use our calculated value of negative 9.02 radians per second in order to find the time. So then all we have to do here in part D is use the formula. Well, we can use alpha is equal to omega, delta omega, so that's omega final minus omega initial over delta t. So that means that t is equal to omega final minus omega initial over alpha. And if we plug in those numbers there, we get 27.4 seconds. As we talked about earlier, translation and rotation equals rolling. So if we take translational motion, for example, we're just looking at this disk and it's going to be translating to the right, we could say that all of the points of this wheel are moving to the right with a certain velocity of the center of mass. Then if we were just to rotate it, then the center of mass wouldn't move, and the top point here would move to the right with a speed omega r, and this bottom point would move to the left with a speed also omega r. We know this from our analogy between translational motion and angular motion. So if we add this translational motion vectorially with this rotational motion, what we get is that the center of mass is going to move at the velocity of the center of mass. That's fairly obvious. But this upper point is actually going to be moving faster with a velocity of 2 times the velocity of center of mass, remembering that omega r is going to be equal to the velocity of the center of mass due to our rolling constraint. And so what we get on top is that this point is actually moving with twice the speed of the velocity of the center of mass. Meanwhile, the point down here, you see that there's a vector to the right and a vector to the left. This vector minus omega r is going to be equal to minus velocity of the center of mass due to our rolling without slipping constraint. So the velocity here ends up being 0. This is an interesting result because it actually leads us to a different way of thinking about rolling without slipping. That is that at any moment there's an instantaneous fixed axis of rotation here at point P. When a wheel rolls without slipping, the point of contact of the wheel with the ground is instantaneously at rest. Just for a moment, this point P is at rest, and those points that are closer to the point of contact with the ground move with less linear velocity than these points out here. This point that's farthest from point P is going to move with a much greater linear velocity than any point in here close to P. Of course, if we take this point P as an instantaneous fixed axis of rotation, then omega for this entire wheel would actually be the same for any point. It's just that further out, when we look at the linear velocity, which can be calculated with omega r, the r will be bigger from the axis of rotation, so the linear velocity will also be larger than a point closer in towards P. If you look at this picture, it's difficult to see here, but you can see it more clearly in your book. The spokes on the wheel, actually down here, you can see that the lines are pretty crisply made out, whereas the spokes on the tire here, due to the photograph, are actually blurry. And this supports our previous discussion that the velocity up here is actually going to be greater than the tangential velocity down here. Just a word about friction. In order for objects to actually roll, we need to have friction. That's what's going to initiate the rotation of the rolling object. But when we do have this friction, we can see that friction is always acting parallel to the surface of contact. So in this case, the friction is pointing to the left with the sphere rolling to the right. But the actual motion of any point on the rim is actually either moving up or down, depending on if you're in front of the point of contact or behind the point of contact. This implies that there is no work done by the force of friction, and it implies that when we roll without slipping, the friction is static. We aren't going to lose any energy at this point due to the rubbing between the two surfaces, and we will have static friction. It's worth a mention here too, though, that just because we have rolling, do not plug in that the force of static friction is equal to mu s Fn. Of course, that is the maximum value it can be, and usually when we're rolling, we don't reach that maximum value unless the ball is, or the wheel is about to slip. So just be really careful when you plug in for the force of static friction, that you're not just saying that the force of static friction is equal to mu s Fn. Also, we need to talk about how to use this sigma tau equals I alpha. We can only use this formula when the axis is either fixed in an inertial reference frame. That means, something's like a pendulum is moving where there's a fixed axis of rotation, in which case we have to be very careful that we're using the moment of inertia about that fixed axis. Or we can also use the sigma tau formula when the axis is fixed in direction but passes through the center of mass of the body. So this second option is why we can use the sigma tau equals I alpha statement when we do problems with rolling without slipping. The axis of rotation is generally through the center of mass when we're looking at uniform objects, and that center of mass is moving in a fixed direction. So it's just really important to know the limitations of any formula you're using, and these are the limitations of using the sigma torque equals I alpha statement. We're going to look at another example now, example 10-21, a sphere rolling down an incline using forces. Now remember, when we look at problems of inclined planes, we could look at it from the standpoint of using forces and torques, or we could use it from the standpoint of using energy statements in order to solve the problem. We're going to be doing that in the next video lesson, but for now, let's try to solve this problem just using forces and torques. The question reads, analyze the rolling sphere in terms of forces and torques. In particular, find the velocity v and the magnitude of the frictional force, and they call it F sub Fr here. We know in this case, since we're rolling without slipping, that frictional force is going to be the force of static friction. Just be careful again, we cannot assume that the force of static friction is equal to mu s Fn, only that the static frictional force is less than or equal to mu s Fn. So we need to be cautious in using that formula. In this problem, our goals are going to be to find an expression for the acceleration, A. We're going to try to find the final velocity when it's at the bottom of the ramp. We're also going to try to find the magnitude of the force of static friction. So we're going to start this problem by drawing our free body diagram. So we have the force of gravity pointing down. We have the normal force, which goes through the center of mass of the object of the sphere, and we also have the force of static friction. We're going to pick a, well, because this object is going to be accelerating down the ramp like this, we are going to pick a coordinate system that goes along with that. So down the ramp and up off the ramp is going to be positive. we're going to have another dimension, which tells us that when we rotate, we're going to pick actually rotation the other way. So actually, instead of doing out of the page as positive, we're going to put the rotation axis back off into the screen here. So that means that when we have a clockwise rotation, we're going to say that that's a positive rotation. So we're going to start by writing our sigma f statements, and then eventually we're going to have a sigma torque statement. So we'll start in the y direction. Sigma f in the y direction is equal to 0. Acceleration in the y direction, or off of the ramp, is equal to 0. And so that's going to be equal to Fn minus the component of Fg that's perpendicular to the inclined plane. So that'll be Fg, or mg cosine theta, where theta is the angle that the ramp makes with the horizontal. So we find from this that Fn is simply mg cosine theta. In the x direction, we have sigma f in the x direction is equal to m times the acceleration down the ramp, which equals mg sine theta minus the force of static friction. Okay, now at this point, you might be tempted to plug in that Fs is equal to mu s Fn. But remember, that is a boundary condition for when the sphere would be about to slip, and that is not necessarily the case here, so we can't plug in mu s Fn for this force of static friction. So we need to look at another equation in order to try to get rid of all the unknowns that we have. So what we're going to do is actually write a sigma tau statement, and one of the ways that sigma tau can be used is if we're rotating around the center of mass, we can use the sigma tau with the fulcrum at the center of mass. So I'm going to look to see how the forces contribute to the torque in making this rotate. So we have sigma tau, and let's first consider the force of gravity. Fg does not contribute a torque because the line of action goes through the fulcrum, and that is also true of Fn. The only force that contributes to the torque is this force of static friction. And the force of static friction is actually going to cause it to rotate in a clockwise direction. So that's going to be a positive torque. So the sigma torque statement is going to be equal to I alpha, which is equal to the torque due to the force of static friction, which is positive Fs, times the lever arm, which is going to be the radius of the sphere, which we'll just call r naught. If we look it up in the table, the moment of inertia of a sphere is simply 2/5 m r naught squared times alpha is going to be equal to Fs r naught. We also know, if we have rolling without slipping, that this alpha is going to be acceleration, the linear acceleration of the center of mass over the radius. So in fact, what ends up happening is that we get that the force of static friction on this side is simply equal to 2/5 ma. If we substitute that into our sigma f in the x direction equation, what we'll get is ma equals mg sine theta minus 2/5 MA. We can cancel all the m's out of here. So this m goes away, that m goes away, that m goes away. And I can bring this 2/5 a to the other side, so I get actually 7/5 a is equal to g sine theta. And when I solve for acceleration, I get 5/7 g sine theta. And that's the acceleration, the translational acceleration of this sphere rolling down the ramp. Now, if you want to compare that, if we have an object that is just sliding down a frictionless incline, we would get the expression A is equal to g sine theta. You might remember that from last year. So you can see that the acceleration, because we have rolling, is going to actually be less than if we had an object that was just sliding down a frictionless incline. In order to come up with the velocity, the final velocity of the sphere as it hits the end of the incline, we're going to take a look at using kinematics. We know that the v initial is equal to 0, and that our acceleration is this 5/7 g sine theta, and we have to find our delta x, which is, if you do a little bit of trig, is equal to h over the sine of theta. So we're going to use the formula, of course, v final squared equals v initial squared plus 2a delta x. And when we rearrange that formula, what we get is that the final velocity is equal to the square root of 2a delta x. So that is equal to the square root of 2 times a, which is 5/7 g sine theta, times x, which is h over sine theta. This is a capital H based on our diagram. And so what we get is we have this sine cancels out, and we get the square root of 10/7 g times h. So that's the final velocity when it reaches the bottom of the ramp. The last thing we set out to find was the force of static friction, which we can just use this formula, which said that the force of static friction is 2/5 times m times a. We know that a is equal to 5/7 g sine theta, so when we plug that in, we get 2/5 times m times 5/7 g sine theta, and we get that the force of static friction, Fs, is equal to 2/7 mg times the sine of theta. This result tells us that if the coefficient of static friction is sufficiently small that it can't get up to this 2/7 mg sine theta, or if theta is significantly large, so that the force of friction is greater than mu SFN, then the sphere will not only roll, but also will slip as it moves down the incline. And we'll see problems like that probably next week. The final example we'll be looking at is example 1023, a falling yo-yo. Although this may not look like a typical rolling problem, it is, because the string is going to confine the cylinder to roll in a certain way without slipping. A string is wrapped around a uniform solid cylinder, something like a yo-yo, of mass m and radius r, and cylinder starts falling from rest. as the cylinder falls, find its acceleration and the tension in the string. We're going to assume here that the cylinder does not slip from the string. I want you to try this problem on your own before you look at the solution. Write a sigma F statement, a sigma tau statement, and use the rolling constraint in order to solve. So pause the video now and try to solve this on your own. As always, we're going to start solving this problem with a free body diagram. Of course, there is the force of gravity coming from the center of mass of the cylinder. And the only other thing touching this cylinder is the force of tension. So we can write a sigma F statement. Sigma F is equal to, let's actually pick down as positive here. And we will pick this direction clockwise as our positive rotational direction. So sigma F is equal to mass times acceleration, and that's going to be mg, the force of gravity, minus ft. Okay, now we're going to choose our fulcrum to be the center of mass of the cylinder, and we know from looking at our chart, and we derived it last week, that the moment of inertia of a cylinder is equal to 1/2 m r naught squared. So when we write our sigma tau statement, I have sigma tau is equal to I alpha. And if we place our fulcrum at the center of mass, then the only torque on this object is the force of tension times the radius of the cylinder. Plugging in for the moment of inertia, we get 1/2 m r naught squared times alpha is going to be a over r naught, and that's equal to r naught ft. When we simplify that and we get rid of all these r naughts, we get that the force of tension is equal to 1/2 ma. Let's plug that back in to our sigma F statement here. So I get ma is equal to mg minus 1/2 ma. I'll bring this last term to the other side and get 3/2 ma equals mg, or a is equal to 2/3 g. That's a little bit less than the actual acceleration of gravity, 9.8. It's 2/3 of that value, and that kind of makes sense because there's going to be this string that's preventing it from accelerating at g. Finally, when we want to find the force of tension, we're going to plug this acceleration back into this formula. So we'll get Ft is equal to 1/2 m times 2/3 g. And so Ft, the force of tension, is going to be equal to 1/3 mg. That concludes our video on rolling without slipping. If you have any questions, make sure to write them down and bring them to class tomorrow. See you there.